Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Today we go all the way to Brazil. And so it's no longer North Atlantic, now it's South Atlantic seminar. And our guest today is my nephew, Gilles Gonçalves de Castro from Florianopolis, and he will tell us about infinite time relations in sister algebras. Gilles, the floor is yours, the Zoom is yours, take it away.
Okay, thank you for the invitation to give a talk here. So this is a project that I've done with Julian Boave, I think a couple of years ago, and we're still trying to look for some interesting examples to apply our theory. Of course, we have the classical ones, but we're still looking for some new interesting examples. And the idea is to talk a little bit about universal system algebras. So to give a little bit of motivation. Usually back in the 70s, 70s, even the 80s, a little bit in the early 80s, when people define sister algebras, they usually, they usually give some operators in a Hilbert space, and they wanted to satisfy some relations. So, for instance, there's this algebra that you want to generate by finite isometry. There's the Kuntz algebra, Kuntz algebras, and they really defined you really using operators in a Hilbert space. But when you define like that, there's the problem that kind of depends on basically on the representation on the real operator that you're looking at, and the question is if this algebra is uniquely defined. So usually not really, but there are some results that you can give us some kind of uniqueness theorem to prove that under certain conditions these algebras are unique. So for instance, in Coburn's paper where he is talking about sister algebra generated by isometry, if the isometry is actually a unitary, then the algebra defined is just a complex, the continuous function on the circle. But if it's not a unitary, then he proved that it doesn't depend on the isometry. So it's what we know nowadays as the topless algebra. But he has to prove that independently on the isometry they choose, as long as it's not unitary, the sister algebra that is generated is all the same. So the same thing that happens for the Kuntz algebras. So he defines as an algebra generated by certain isometries, satisfying a certain relation. And in his case, he proved that the algebras are simple. So independently, again, on how you represent the algebra, on which operators you choose, the algebra is going to be always the same. As for the Kuntz algebras, actually, this is not always, there is not always a uniqueness theorem for the Kuntz algebra. They use a condition on a matrix to give a unique theorem. But then, so if it's not unique, the idea is if you can find a universal version of these algebras, in the sense that all represented versions are quotients of this universal one. And this is something that I think it's probably kind of this folklore at the time. And Blackadar in 85, he wrote, I think it was the first part of one of his papers, describing how one can do this. So how to build a sister algebra out of some relations. So I'm going to explain his ideas. We're going to generalize a little bit what he's actually done in his paper. This is a little bit of the motivation on this topic. So for instance, the Kuntz algebra we built using a matrix of zeros and ones, and then it was an example in Blackador's papers that you can consider. So this Kuntz algebra, the universal version, so the algebra generated by partial isometries, which satisfies this relation. So I'm going to explain exactly how we want this relation to work, but this was one of his examples. But in the Kreutzberger paper, they also considered the case of an infinite matrix as well. So because they are considering represented versions of the algebra, so they can have infinitely many partial isometries. That's not a problem. Satisfying these relations. I guess in the stronger operator conversion sense. But when you try to describe this as a universal state algebra using the version of the universal state algebra that Blackadar developed, there's this paper by Axelot where they do this, they extend the construction of the quantitative algebra for infinite matrices. But there they say that the theory that universal state algebra, this is a state that in the paper that it breaks down when the relation involves the strong topology. But that's not really what Blackadar said there in his paper, just because he just developed just a part of the more general theory. But I think that people got the impression that infinite sums would be something that we can't do when we want to define a universal state algebra. But then, so we try to develop and see if it's really can be done or can do this. Another instance where this happened. Yes.
So at this moment, we don't know how to understand this relations involving the strong topology in the universal sense, yes? It's only as already represented in B of H, yes?
Yes, at the time there, yes. So our paper, we develop at least part of this on how you can do this universally. That's what I'm going to explain during this talk. Yeah.
This would be our goal. Okay. Okay.
Yes.
Okay. Thank you.
So other interests where this infinite sum were avoided. For instance, when we define graph-system algebras, the first papers that where they define they use finite graphs, and then they have this condition of being the graph being row finite, because we wanted the relation to use the edges that leave a certain vertex, and if there are infinite many edges leaving the vertex, we do need an infinite sum. So the first versions of the graph-system algebras didn't allow that for that to happen, and then had to go through to the theory and try to define a different way of defining the graph system in a way that it allows for these conditions not to be held. We don't need row finite to define the graph system algebra, but it was something that if you allowed for this infinite sum, you could define it directly, but since we don't, we have to look at a different way of approaching this. Another instance where this happens, this is something that Julian Bach, who's my co-author, he did his PhD thesis on this. It's the sister algebra of the integral domain. It's a paper by Kuntz and Lee. There again, they define these algebras of the integral domain, but they impose some conditions on the integral domain in order for some kinds of sums to be finite. So there is these quotients by some ideals. They need these quotients to be there be finite many classes for this quotient in order to, when you define the sister algebra, you have a finite sum. But so the idea is, well, can you try to remove this condition? And then so that's the question that try to answer. Do we really need to avoid this relation involving a stronger operator topology? And if you look at the Blackdar's paper, when he's talking about this universal state algebras, he actually says that in theory we can consider any relations that can be formulated if we're operating a Hilbert space. We can define this universal version, but he only developed really for some kind of relations, which in our paper we call this non-relation, just to differentiate between these strong operator topology relations. So this is what was done in his paper, and something that here in Florianópolis, I think because of who we learned this as students. There are a lot of students that wrote this as an appendix or on their master thesis. So it's something that we learned, but I think it's not something that I don't know. It feels to me that it's not something that is universally known. For instance, I'm working on another paper, and then I have one co-author that he did his PhD in New Zealand. And when we are just defining a sister algebra associated with a subshift, and he asked if you need to prove that there is a universal representation for the relations that we're giving. Then we said, no, we're actually, since the relations this is no relation, this is something that it's done. There's another co-author again from South Korea that she defined this sister algebra for Boolean dynamic systems, generalized Boolean dynamic systems. And again, in their paper they prove that there exists a universal representation, but that's actually not needed to do because it follows from the general theory or from Blackadder. So as I said, even if it's a paper from the 80s, I feel that it's not really well known, but it's something that we at least here in Farnops we learn because of Hui, I guess. Okay, so how we're going to define these relations and then the universal sister algebra. So the idea is that you're going to have a set G, which is, well, G for the generators. And then since we are dealing with sister algebras, you need this star of these elements of the generator. So I'm just going to write this as a disjoint union of these original sets. And then we can take the free algebra generated by this set. We can think actually, we can think this as you take this union, take the free semigroup generated by this union, then they take the same group algebra of this free semigroup. We don't ask this to be unital, so you're not taking the free monoid, just take the free semigroup. And then you have these universals, the pre-star algebra, obviously generated by the set G. So there's a very natural involution that we can define, just saying the generator to the start to the original generator, and then use the complex conjugation for the evolution on the scalars. And so we consider two kind of relations. So this normal relation, this is one that was done in Blackadder's paper. So basically, you just take this linear combination of multiplications of elements on G and G star, so basically an element of this pre-algebra, and then you have a number, positive, non-negative real number, and I'm going to show you this in the next slide, but this is to be interpreted as being that you want the norm of X to be less or equal than this eta. So this is, want this to hold in the sister algebra. This is what this means for this pair. Usually we have relations being as equalities. So what we can do is just put everything being equals to 0, and then you have this element of the free algebra being equal to 0. So we can put this eta to be 0. So the equality relation that we are using to when we find sister algebras follows from this theory when using it equals to 0. And then we put another kind of relation, which is we call that in our paper this SOT relation for the strong operator topology. And here we're just thinking, because we want to be working infinite sums, we are doing just a specific kind of relation, which is just a net on this pre-algebra, and this is to be interpreted that this net converges to 0. So that's the kind of relation that we are using. So when you have an equality using infinite sum, we can interpret that as a net being converging to 0, and that's why we consider this kind of relations. But again, Blackadder's paper say that we can do things more generally if you want to, but we just developed this for the purpose that we're thinking. And then just to use it later in the results, we call it generating triple, just the set G, which is the generators, and then these two kind of relations, the normal relations and the strong operator topology relations.
Oh, sorry, R plus contains 0, yes?
Sorry?
R plus contains 0, so you
yes
drag relations.
Yes. So this is non-negative real numbers. Okay, so we want to represent these relations in the Hilbert space of sister algebra. Because we want to deal with the strong operator topology, we're going to represent these on Hilbert spaces. And the idea is that as far as the algebra goes, just a star algebra homomorphism from the three star algebra generated by G in the boundary operator on a Hilbert space. And then the two things that I said, that we want to interpret that that pair X eta to be the norm of X being less or equal to beta, but then the representative version of this X. And the second one would be this S limit to be interpreted to be the limit with respect to this strong operator topology. Then this went to goes to 0 for every net these other kind of relations. Okay, so we want to build a sister algebra from these triples, and we need not always we're going to be able to do that. Then we have this notion of admissibility for the relations, which is something that again this is done already in Blackbeard's paper, and the idea is that this triple here is going to be admissible if whenever we have a family of representations of the relations. The direct sum of the representation is again a representation. The issue here is that it could happen that if the norm of an element is not bounded, because this happens only for elements X that are pairs in the relation, but for other elements in the free algebra, it could happen that the norm of the representations goes to infinity, and then when you take the direct sum, this direct sum actually is not going to be a bounded operator, so it's not well defined. So that's way of looking at that. So for this to be admissible, we want this direct sum of representations again to be a presentation, and then we want to well, first we give a sufficient condition for admissibility. In the case of norm relations, it's sufficient necessary. We couldn't prove that this is necessary in this case of a strong operator topology, and I think it's not really necessary, but it's just sufficient in this case. So the idea is that we can find constants for not for all elements of the free algebra, but a constant for each element of the generator that bounds the norm of G for every representation, and we want also for every net on this strong operator topology, we also want to find a bound for the norm of any element of the net being uniformly bounded by this at X here. So if you don't have the strong operator topologies, this is so. First, before that, if you have these constants, then the trip is admissible, and if you only have the norm relation, then this condition actually is also necessary. So, and that's how we learn here when we learn this universal star algebra. We at the first we even give this a definition of admissible, but this is only equivalent for the norm relations. And then using the direct sum of representation, that's the original definition of Placidar, and that's really what we need when we build this sister algebra. This is as far as we tried. These conditions on the norm is not enough for really to build the sister algebra. So what's the idea? The idea here is that when you have these conditions, we can actually define a same norm on the free algebra. So that's how we do this. So yeah, so we consider the C-star same norms on free algebra that comes from representations of the triple. So this is easy to show that this norm, if we never have representation, then this norm it's a C-star same norm. And then the idea is that whenever you have this admissable generating triple, then the supreme of all the same norms for any element of the free algebra is bounded. So as I said, in the original definition for norm relations, you only need to ask this for the generators, and you can easily prove that this holds for all elements of X of the free algebra. But we need to take care of when you try to define this. When you want to prove that the relation holds for that limit, then we need to take care of that in a different way. So that's the idea. So we take all the same norm that comes from representations. We can also, there's just this theoretical problem here. We wanted to take the supreme of our representation. Our representation is not really a set. So in order to avoid this, I think this is something that also Luis does when he teaches us for his cross product, all the stuff that we are avoiding take the supreme of our representation, which is not a set, it's just a class. So we can consider just the set of same norms, because D here is just a set of functions. So there's no problem of dealing with this supreme indexed by the set. Okay, so and if the supremum is bounded, then we can define a C-star same norm in the free algebra generated by G. This the free star algebra by G. It's just taking this supremum over all of P. It's quite straightforward to show that this is actually a C-star same norm. And then it has this problem because we want a C-star algebra, not. So we need a C-star norm, not a C-star same norm. And what we do is just take this, whenever I said have the C-star same norm, we can take the ideal of the elements which has this same norm being equals to 0. We take the quotient. There's a norm that we can define in the quotient, which is when we learn about quotient of C-star, this is the kind of norm that we define. And then we're gonna have a star algebra with a C-star norm, and then what we need to do is take the completion respect to this norm, and then we obtain a C-star. So as far as complete construction of this universal C-star algebra, this is what we do. In free algebra, take the C-star same norm, take the quotient, and then you take the completion respect to the C-star same norm. And then we're going to have a natural star homomorphism between the free algebra inside the C-star algebra, which is not really always injected, because here, when we take the supreme, we just need to ask if there exists a representation, and there's always the zero representation, always satisfies the relations. So it could happen that that's the only representation that we have for the relation, this triple, and then we will obtain just the zero C-star algebra, even though we start with some generators in relation which is not empty. So this map I here is not always injected, but there's always a natural way of looking at elements of the free algebra. Just look at the expression inside C-star algebra. This makes sense. Of course, two different expressions could represent the same element there. So
sorry, formally you can always take some relations which contradicts each other, yes?
Yes.
And then you would obtain zero C-star algebra.
Yes. Yeah.
Okay.
Okay, so we want to, when we want to work for this universal star algebra, usually what we want to do is want to take the some certain elements which are indexed by the generators and look at it then at a certain C-star algebra. We want to show that these elements satisfy the relation defined the C-star algebra, and then we would find a homomorphism from the universal one to the C-star algebra that we find. For instance, for graph, they usually call this the E family, or the Kuntz-Krieger E family for a certain graph. So you have these families, then you can build a C-star homomorphism that's because that comes from the universal construction. But now, because we are dealing with strong operator topology, this only makes sense on a sister algebra when it's represented in a Hilbert space. So for us, this is a little bit more. We need a little bit more work to build a homomorphism from the sister algebra. This universal sister algebra of the triple, in that we want that not only we have this star homomorphism, but we also have a representation, a faithful representation of the algebra on a Hilbert space, in such a way that when we compose this, we have a representation of the triple. Because here in B of H, it makes sense to talk about strong operator topology. In A by itself, not really. Of course, this can depend on the representation. Have different paper representations where for some this composition is a representation of the triple, but for other composition it's not. So we have to find a nice one to work with if you want to build a sister homomorphism from the universal one to a given sister algebra A. So that's something that usually when we are building a sister algebra of some combinatorial objects, there's always the question of, can we find a nice paper representation? And usually this nice one that we can find works for this construction. I'm going to give an example later, but basically, yeah, we need this paper representation, and sometimes this paper representation is already there, depending on the construction. And
sorry, you don't assume that phi is injective, yes? Do you?
Phi, no, just phi.
Okay, just any star homomorphism. Okay.
Yes, just a star homomorphism. Because you could take a quotient here. Could be that, yeah. So the universal one is kind of the largest one, and they could be a quotient. So it's not injective.
Mm-hmm.
Okay, so as I said, to build a star yeah, for the representation that's fine. But when we want just to represent the generators on a sister algebra, then that's easy because we just need to tell which elements correspond to each generator, and the universal property of the free algebra and the free star algebra already gives us a star homomorphism from BG to A. So at least when you give the elements, at least this map phi is easy to build. You just need to tell what is phi of G for every element on the generator set.
Sorry, just a stupid question. If there exists a faithful representation pi such that blah, 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 then I understand that for any faithful representation, it will also, this pi composed with phi will be a representation of a generating triple, right? No,
that's not true. I'm going to give an example of that, but that's not true. It depends on the presentation. So to build the sister homomorphism, we need a nice one. It is not hold for any representation. But I'm going to give an example later in the talk.
So maybe the problem is for the usage of the same word of the representation, since representation in this case of the sister algebra is just a star homomorphism into B of H. But the representation of this triple means something else, means the relations involving norms and so on. So
yes.
In somehow different flavor, yes?
Yes. So the presentation of the triple, yes, you need not only the elements there in B of H, but you need that the relations are satisfied there. And that's going to depend on the Hilbert space and how we're looking at the elements there. Yeah, so and then the other question that we
I see.
If we can find a nice representation of the sister algebra to just build that actually satisfies the relation, and then we can do that. There's this kind of universal representation that we build there. But yeah, so as I said, contrary to what happens if you have normal relations, and not all presentations of the sister algebra on a Hilbert space are gonna satisfy the relation of the triple. So because it kind of depends on how we look at the strong interpret topology in B of H, and this is going to depend on the Hilbert space that we're choosing. Nevertheless, we can use this universal representation that we find to build a homomorphism from sister algebra A to this universal one. I'm going to give an example later in the talk here as well. Yeah. So
I is this canonical map, right?
Yeah, I is that canonical map from the free algebra into the Hilbert's into the sister algebra.
Sorry,
okay,
could you say how big this HU is? How large it is?
Basically, I think we have to, if I recall correctly, it's just we take a direct sum of representations from. I'm not sure if it's. I think it's for each element of the free algebra. I think it's not really that big because we just need to show that there's enough representations for these elements of the star algebra to be different from zero because we want to be faithful. But I think we, if I recall correctly, we just take elements of the free algebra and take some kind of genetic construction there and take a direct sum, and this is going to work out.
So once again, it's a direct sum over all generators or all elements?
I think it's going to be overall elements of the free algebra.
So
I have to look at the paper, but if I recall correctly, it's
if it is true that for all elements you take one summand in this direct sum, you would get something which is non-separable. Yes.
Yeah, I guess yes. We could have something that's not separable. But yeah, that's an interesting question. If this is algebra separable, you can find a universal one that's also separable. But I don't think we have looked at that.
It is so for universal GNS construction. So if you take a really universal GNS construction, then this is some huge Hilbert space. But if your sister algebra is separable, then you can find a representation which is faithful and it is also represented on a separable Hilbert space.
Yeah. Yeah, my guess is that this is going to also hold here, but we haven't proved that. I suppose that's going to work out.
Okay, thank you.
Okay, so for some examples, going back to the Kuntz algebra, we have if you take the Kuntz algebra ON, where n is finite, then you have this, well, we have n isometry satisfying that the sum of SI SS star is equal to 1. And this implies that the final projections of these isometries are orthogonal. But in the case of O infinity, because at the time we're not really looking at this infinite sum, when it was defined the sister algebra O infinity, he just asked for isometries with final projections, orthogonal final projections. And then, well, so the idea is, can we define a sister algebra so allowing this infinite sum to be equal to 1? So that's one of the examples that we gave, and the answer is yes. So the first thing is you have to interpret this infinite sum being equals to 1 as a net conversion to 0. So you just take this 1 minus the partial sums. And because we want to the sort of unit, because we want to have isometries, we also need these extra generators to represent the unit here, which is something that yeah, we really didn't need in the Kuntz algebra, but it's nice to put a unit there. And so you need the relations that says that this one is extra unit. So 1 ti equals ti, ti 1 equals 1 equals ti, and etc. And well, we want this to be isometries. And then the other one is, as I said, is just this net to represent that this infinite sum equals to 1. So if I had this triple, prove that this actually is the original Kunz algebra. So the first thing is, well, in this case, because the Kunz algebra is simple, you just need a surjective C-star homomorphism. Which is not 0, and then it's automatically going to be an isomorphism because there's no kernel here, and then we prove that this, as for the finite case, which is something that we can prove, as I said before, if this sum goes to n, this v equal 1, we can show that these projections are orthogonal, but the same thing holds even we take this infinite sum. So even if you take consider the infinite sum of projections being 1 in the strong operator topology sense, again, this projection is going to be orthogonal. And so this is going to imply, because the finite projections are orthogonal, is going to imply using that universal representation of the C-star algebra, that the represented versions of these Ti and Tj is going to be orthogonal. And because this holds for the universal representation, which is faithful, this is going to hold in the C-star algebra. And so for the universe, by the universal property of infinity, using the theory of Laplace theory, or just using normal relations, we have this unit of star homomorphism from the infinity to the C-star algebra in such a way that we have this phi of si equals ti for all I. Of course, yeah. So because this generates the C-star algebra, Fi is going to be surjective. Well, we also need the unity, and yes. I guess you have to show that there's a representation where these TIs are not 0, so this the kernel can't be the whole Kunz algebra, so it has to be 0. And then because of that, you can find this is isomorphic. We could do. I'm going to do this for the Exolac algebras, but we can also build a homomorphism from the C-star algebra to infinity as well, using the universal property of the C-star algebra. But here it's more a little bit more straightforward because we have the Kunz algebra is simple.
Sorry, I'm a bit confused. I'm a bit confused by your statement whether rho u is the faithful representation. So is it something canonically fixed? Can you tell me what is this the faithful representation, not a faithful?
Yeah, so this rho u here is the one that I have in this theorem. I guess
okay.
Yeah, I guess I called pi u here, but that's this representation here that I'm considering.
But this representation pi u is unique?
No, it's not unique, but it's concrete, I guess. So it's there's a concrete description of this pi u, but it's not uniquely defined. There's any faithful representation where these relations are satisfied as long as there exists one. I think they work out. I guess you're correct.
Okay.
Put
So
a faithful representation.
Well, yeah, but not any faithful representation, but this faithful representation from theorem earlier on. Yeah.
Yeah. So it should be a faithful representation such that the triple is represented, I guess.
Yes. Exactly.
Okay, so yeah, so here we have the design isomorphism. So it just to show that we could consider the infinity using the same relation that we use to define ON, and not give a different definition. Just the interpretation of the sum is going to be with respect to the strong operator topology.
But
and
you
then-
know, but you have 90 minutes, not 60. You remember?
Yeah, I might be going a little bit too fast, but
Because I see the number of slides and you still have like 51 minutes left. So
yeah, so I can try to go a little bit more slowly.
exactly, there's no need to rush.
Okay, so for that question, that is any paper representation of the sister algebra satisfy the relation? And here we can see that this is not true. So we can easily represent O infinity because for infinity we just need isometries which have the final projection being orthogonal. But if the sum of the final projections is a projection on a proper subspace of H, then this direct sum is not going to hold in this different H. For instance, if you just shift this, you take this representation. Yeah, if you just take this. Yeah, you take this map here and then represent O infinity, even if the original, if you compose with a representation where this is satisfied for this the second copy of O infinity, it's not going to be satisfied for the first copy because you're going to be missing the part of the projection, the subspace with respect to the first isometry. So that's one thing that's it's not really nice about this construction, because usually you want any great representation to satisfy the relation, but not this is not true in general. And this is a nice simple example that shows that. So we need to work a little bit more of that. Okay, so for the other example, the Axel-Laka algebras. So I'm going to explain this relation, but just look at that. We need a lot of things to define this Axel-Laka algebra. But you should go back all to the beginning for talk about the Kunst-Krieger algebra. Where was it? Here. So this is much simpler than all that list of relations that Axel and Laka found. And the idea is, can we define this Kunst-Krieger algebra for infinite matrix just using the same relation that Blakada used before, just to replace n with infinity? Of course, we show that we can do that. When the question is if we're going to find something different or the same thing that Axel and Laka found before. And so they had to really work out how we can reduce all the infinite sum, but not really using this infinite sum. And the idea that they showed, first of all, they want this, instead of looking at isometries, they look at partial isometries. And basically what the projection, both the final projections, actually this is the initial projections, went then to commute. So that's one of the relations they ask. Again, we want that final projection to be orthogonal, whenever they're different. And then there's this kind of commutation. Actually, not really commutation, but yeah, if you think that this SI star SI is going to be that infinite sum, it's basically replacing this infinite sum, this with the infinite sum, and then because the projections are final projections are orthogonal, every thing is going to cancel out, and the only thing that's going to survive is this Aij, STJ, SH star. So this is one of the relation. This is somehow holding that infinite sum relation, but then I have this one. I still have a little bit of trouble understanding exactly what this is representing. But the idea is that we're gonna have these and this kind of regulations. So how we do this is we take finite sets of this index set I. So I can be any set, and then we have this product here of elements, which is in the I guess the J column. Then you take the elements with respect the rows indexed by X, and then we just take the opposite. So if 0, 1, we take the other one for the rows represented by Y. And then we multiply everything here, and we want this to be 0 for all but a finite amount of J's. So the idea is because if you have this different from 0 for finite amount of J's, then when we take this sum on the right side, this sum is going to make sense in the finite usual sense. We don't need to take infinite sum here. It's going to be a finite sum because mostly going to be 0. And we want this sum to be equal to this product. What I said is it looks a little bit artificial, but it's the thing that they worked out in order to code that infinite sum without looking at infinite sums. So take this finite set here, then have finite sums, and then have this product here. So it's just a way that we're gonna replace that sum that had at the beginning. This one sum here. They replace this sum using these sets X and Y with a lot of relations codifying this, but then using unfinite sums. Okay, so that's their definition of the algebra, and because we are using.
Do they assume that this set of indices I is it most countable?
No,
no,
it can be
arbitrary.
Yeah, any cardinality.
Any cardinality, yes.
Yeah. So if you look at this relation, there's this tilde here, and then I'm writing here that's University algebra that defined by family partial symmetries and a unity. So this is the unity version of the XLAC algebras, because this relation here, we are using the one here. The fact is that if we could rewrite, as long as X is not non-empty, we could rewrite this left-hand side of the equation without using the one, because we can just put this X star X here, and then we don't need the one. But if for some Y, the A empty set of Yj satisfies the relation that's known as 0 for alpha but finite amount of J's, then we need the unit to write this relation, because if it's empty, we can't avoid using the unit. So that's actually it's an equivalent condition for the other version of the XLAC algebras to be unitable. Okay, so that's the relation that they found. Then they describe this using partial cross product, and then in a later paper they study the gamma states and all that. That's one thing that I like to, when I think about this kind of stuff. If you look at the original considered algebra related with this subshift of finite type, then basically what is as partial isometry is doing, Sj is kind of gluing a j at the beginning of an element of the subshift, and this Sj star basically what it's doing is removing the j, as long of course it starts with j. But because of the matrix if the entry of the matrix is 0, we cannot glue. Let's say if Ij is 0 and then have a path that starts with j, we cannot glue I at the beginning because here Ij is 0, so have a forbidden word. That's what it appears here. So basically, this is saying that if you can remove J and then we can glue I, it's the same thing as just removing. Because here we remove J, then put J back, then we put I, then remove I. And this can be done as long as AIJ is equal to 1. Then this is going to hold. So there's a very nice way to interpret this using partial action, but I'm not going into detail here. My goal here is trying to describe this algebra using these infinite sum relations, and really to give some much more simple relations than that list that they gave there. And to be closer to the definition that Catarina gave for the University of Kunstgebiet algebras. So that the idea is again to consider the partial isometries indexed by the set I. I'm gonna take the unit because it's the unit of version. Then I'm gonna talk a little bit later about the non-unit of version. And then the normal relations. Just the one that says that these are partial isometries, then one is a unit. And we're going to have two kind of relations using this strong operator topology using infinite sums. So these are the two. So one is just saying that we want the sum of the final projections to be equal to 1. So basically the direct sum of the subspace is going to be the whole space, and the second one is the one that is the same as in Blackboard space. So all these relations should be understood as a net, as you explained at the beginning of your talk, and then you take what ti star minus 1, and then you treat it like a net which is directed by all finite subsets, yes? Yes. This is going to be in the next slide. That's correct. Yeah. Take the direct set of all finite subsets of I, and then the net is going to be indexed over that.
Okay, thank you.
But I'm confused by your statement that saying that TI is a partial isometry is a norm relation. Could you go back and show me again the definition of a norm relation? Okay, so a norm relation is just a pair. Yeah. Let's see if I can write. I don't have my graph tablet here, but let me see if I can. So let's say you have a relation that say that S star S equals S. So that's the relation that we wanted this to hold in the C-star algebra. So how do you interpret this equality as this pair? You just take the usual difference between these two things. Because then we want this to be 0, then we just take this to be 0. Because if this norm of this element is less or equal to 0, then it's going to be equal when we take the C-star. Yeah, thank you very much. This is exactly what I wanted. Thank you. Perfect.
Yes, and this is the reason why I was asking about whether R plus is contains 0.
Yes. Let me just go back here. Let's get it to clear.
Sorry, maybe a stupid question, but even if you don't allow this 0 to be present in R plus, still you can take the sequence of such relations and take eta to be 1 over n, and the infinite sequence would give you the same. Yes, this relation. Okay.
I'm just so familiar with a relation being equal equalities that I don't have an example where eta is different from 0. But I think in Blackbird's paper he has some examples there where it is non-zero for some kind of relation there. Okay, so going back here. So that's the relation that we had. So this is to be interpreted as being that net. If we can write this, I think I just written this in the paper. Like I said, I guess we can, as we explained before. So this is we interpret as being 1 minus all finite sums directed by the partial, the finite subsets of R. Okay, so one of the things that we proved in our paper, that's the sister algebra defined by this triple. First of all, we have to prove that this triple is admissible. That's something that we do, because these elements are going to be partial isometries. These Ti star are projections. And basically what we're doing, we take, and it's going to be projections that's going to be less or equal than 1. And they are orthogonal. We prove all this kind of stuff. So when you take 1 minus a finite sum, this is always going to be bounded by 1 because it's going to be a projection as well. So these relations are admissible using that sufficient condition that all elements of the net are bounded by 1, both in both relations. Okay, so for this case, because this algebra is not always simple, when we're gonna build this isomorphism, you're gonna build the 2 maps, one from the Exolac algebra to this universal one, and then the other from the universal one to the Exolac algebra. The first one is from the Exolac algebra, and then the idea is that we use that universal representation, one of the spherical representation that satisfies the relations for the triple, and then we show that this Exolac algebra relations are satisfied for these elements of the family here, which is something that I think the Exolac already did. They already talk a little bit about that in their paper when they're trying to motivate their relations. They kind of look at this, how if it was represented, how things would work out. And then the idea here is because these sum are with respect to the strong operator topology. When you're going to prove this relation here, what we do is just take an element of the Hilbert space, and then we just compute this, or replacing this Si by the P, the row of Ti, and the same thing for the stars. So we look at the represented version of the Ti's inside that paper representation, and then apply it at an element of the Hilbert space, and then we use these 2 relations to show that these work out fine. So all of these things that we do here, because here, for instance, we, as I was saying before, we really wanted that Si star to be equals to this sum. So if you put and multiply by, let's say, Tk star, the only element in the sum that's gonna survive is when j equals k, then it's gonna give us exactly what we have here. Because it's a partial isometry, then it's gonna survive everything. Then this really is just that in sum. The same thing here for the commutation relation. We use this infinite sums and then apply it an element of the Hilbert space, and we show that in that represented version of the universal algebra, everything works out fine. So that's the idea, to show how can we show that relations on this sister algebra works out, to take the representation and we apply it elements of Hilbert space, and if it holds for any element, it holds for these operators, and because the representation is faithful, then it's going to work out for the sister algebra as well. And then for the other map, so this is something that we already done for the Kuntz algebra. But for the other map, can we build a map from the University Star to the Exolac algebras? And that's where we need to use that theorem of the kind of the universal property of this University Star algebra, is that we need a certain favor representation, in this case of the Exolac algebra, in order for when you talk about the strong operator topology relations, it's with respect to this representation, to this Hilbert space here. And the operator Exolac already gave they described this representation. Here they're using this PA is the set of paths on because you can think as, again, using a little bit of the symbolic dynamics setting, is that we can think that this is just sequences of elements in the set I, in such a way that whenever you have a pair that in the sequence, the corresponding element in the matrix, it must be 1. So we have all these paths that satisfy this, and you take this the discrete L2 of this set, and you also, if you just take this one, the representation not to be always favorable, but if you take this tensor product of the L2 of the free group, then basically the SI is going to be the thing that just glues I at the beginning, but then you have I as a generator of the free group. So it's going to be just the projection, just the projection on that I. And the same thing for the ISI stars, just remove I from the beginning of a path, and then have the inverse of this I in the free group.
Okay, let me ask you. So first, when you say that PA is a set of paths, you mean finite paths, right?
Yes, finite paths, yes.
And you just treat A as the adjacency matrix, you build a graph, and then you know what a path means. Because in principle, if you don't know it, I mean, what do you mean by a path? But that's the way I imagine. You have A, you treat it as the adjacent matrix, okay? And then you really have a directed graph. And when I have directed graph, I know what the path means.
Yes. Yeah, it's just that instead of looking at paths of edges, when you build a graph, we look at paths of vertices. So it's going to be, instead of being a sequence of edges, it's going to be a sequence of vertex in such a way that each pair is connected by edge. But yes.
But I guess it boils down to the same thing, no?
I don't think so. I think there's a problem that because that's something that because not all Exolac algebras are graph system algebras, and not all graph system algebra are Exolac algebras. There's this. It's similar, but there's a lot different because really here, as I said, when you build the graph and you take the paths, we're not looking at paths as sequence of edges, but we're looking at paths as a sequence of vertices that are connected by edges. That's when we here really it's a path in this sense. Or you can think as if you look at if you have this matrix of 0, 1, you have the natural subshift associated with the matrix, which is sequence where the forbidden words the pairs for which the entry in the matrix is 0, and then just take the blocks of this subshift.
So wait, so in this case, I really would like to hear again what you mean by a path. You mean that it's what, a sequence of vertices such that adjacent vertices satisfy exactly what condition?
So let me write here.
Yeah.
So you want sequences, let's say finite sequences, x1, xn. So this sequence is going to be xi wants to be an element of our finite of our index at xi.
Yes.
And you want that xi, xij, I plus 1, the entry of the matrix of this element must be always equals to 1. So that's the, this should be for all I from 1 to n to n minus 1.
Yeah, I plus 1, yes, is equal to 1.
So that's what I mean by path there.
Yeah. It's funny because I thought that this is exactly what I thought it should be. So I'm surprised that it's not equivalent. Okay, but
yeah, it's kind of weird, but yeah, if you look at as an edge, yeah, adjacency macro for the edge graph, I guess it doesn't really work out always. But it really should think this as a sequence of vertices and not a sequence of edges.
okay. I guess it's still true what I said at the level of graphs. It's just that, as you said, as a graph system algebra, such a graph need not coincide with this Excel-Lacka construction.
Yes, yeah.
But I guess that as long as we're just talking paths and graphs, it's just the same.
Yes. So there's this more general notion of an autograph. Then I think it works out fine. You can do the autograph out of an infinite matrix, and then it's going to be paths in the usual sense. So yeah, so there in the paper they have this paper representation of the algebra, and with that representation we can show that it satisfies both of these two relations, which it's not really surprising because it was the motivation or their motivation to define the system algebra. The relation that they found is in a way, in such a way that this sum should hold. And so because I have this representation where that sum will hold, then we have a star homomorphism from the sister algebra to the Excel-Lacka algebra, the unital version. And well, it is kind of easy to show that these two maps are inverse of the other because we're just taking the generator here, take SI to TI, and we're taking TI to SI, so it's really one inverse of the other. Now for the unital version, or actually not necessarily unital.
Sorry, could you go back? I'm having problems with that. What does it mean that something factors to? I'm used to the phrase factors through. Is it?
I guess it's just that the wrong word here.
It's just a typo. Okay.
Yeah. It's just saying that I'm using that term there here.
Yeah, then it factors through. Yes, okay. I just didn't see this diagram in my mind. Okay.
Yeah. So for the not necessarily unital version, they first just define the non-unital version, or not necessarily unital, as the subalgebra generated just by the partial isometries. So for the universal version, either finite or infinite sums, we take the unit, but as a generator, but then we just look at the subalgebra generated just by the partial isometries. And it can be the case that we recover the unital one, and it can be the case that we don't recover the unital one. And then the condition that we have, going back to that slide here, the condition for the subalgebra being already the whole algebra is the existence or not of a y such that this statement holds for a empty set yj. So if there is a y in such a way that is zero for all finite amount of j's, then the algebra is unitary. And if this is something that I was thinking that I think the whole basically saying that for a certain row you have just a finite amount of ones, then you're going to find these to be true, because then you can for that row I think if you just take y to be I think just the row where this holds, y is going to be just a singleton set. It's going to be, this is going to hold for that one. And I'm pretty sure if it's because y is finite, this is going to be equal. But this is not stated in the paper, but I'm pretty sure that's what happens. But anyway, so if we can write this relation without using the unit, then the subalgebra is non-unitary. But if you cannot, then the subalgebra is unitary. And so the universal system algebra OA, if you want using just finite relation, you have to divide in two cases: the case where there is this y, or in the case where there isn't. So the case where we can write this as without using units of, then is the universal system algebra generated just by the partial geometries. But if you cannot avoid this unit here, then OA also going to use a unit. So the generator is going to be different whether the algebra is unit or not. So that's what I'm saying. So this description of OA is just an relation, depends on whether the algebra contains the unit or not. And that's something that also it's a little more complicated, because you had to kind of know a priori if the algebra is unit or not in order to work the relations. And again, we wanted to simplify this using the infinite sum relation. And that's the version that we found. So, and then here, if you compare to the Black-Duck's description, it's exactly the same thing, just allowing infinite sums. In that the Xalac algebra, no necessarily unitary version, is going to be isomorphic universal algebra. And then we remove that the unit as a generator, and we remove that first that the sum of the projections are going to be equal to 1. And then just say that they have multiple orthogonal fundamental projections in such a way that you have this. The second relation we still want to be true. And so that's what we show. And for me, it's of course much easier to, at least for the definition of the algebra, it's much easier to look at that than to look at these other 4 family of relations. And it depends if the algebra is unit or not unit. So it's a little bit more complicated, I guess. Okay, so that's the 2 main examples that we had there in our paper. And for the last part, it's kind of let's say we don't want to work with the strong operator topology, and we can ask, can we define let's say we define the algebra using the strong operator topology, and can we redefine in a different way using other normal relations? And that's the question that we try to answer. At least we give some sufficient condition for this to be true. That you take the system algebra. Because sometimes what happens is that, for instance, for graph system algebras, you have this algebra generated by partial isometries and projection. Of course, everything is partial isometry, but you have a certain subalgebra there, which is a commutative algebra, which is generated by the projections. So, for instance, in the case of the graph system algebra, it's just the diagonal subalgebra, and that diagonal subalgebra is commutative, then generated by projections, and then the idea is that we should have this commutative algebra generated by projections. We can describe this always as a universal system algebra, using only normal relations.
Hmm.
I think we can actually simplify a little bit here what we do, but let's just explain what's in the paper, and then I'll tell how I think we can simplify. So the idea is that basically what we're gonna do is take all the relations that's already satisfied in this commutative algebra, and then you take the universal algebra using all these relations. So what this means that you take all this linear combination of finite products, all finite linear combination of these finite products being zero inside the system algebra. You take all these this way of writing this being zero, and then we take the relations that say that these PIs are projections and that they are commuted, because you want to commute this algebra here. And the other relation that we want this to hold for whenever this is already true in the system algebra, we want this to be held also in the universal one. And so when you take the universal one, actually this is already going to be isomorphic to the original system algebra generated by it. And I think it's something that I've been working lately, that I think if you take just the projection of the system algebra and look this as a Boolean algebra, then we can define just the relations using the Boolean algebras, which is something that we have done, for instance, for autographs. For instance, we just represent the Boolean algebra. Actually, don't even need the complement to just take the projection of the union and the intersection. And then I think this is going to be enough to give out the relations, but we haven't proved that, but I think it's enough to do it. But anyway, in our case, we can, whenever this commutative system algebra projections, this is always a universal system algebra for the relations, all the relations that are already satisfied for the system algebra.
And A is, of course, not necessarily unital, right? You don't, A is non-unital in general.
No, it can be non-unit, yeah.
I'm wondering how we can characterize locally compact Hausdorff spaces whose sister algebras satisfy a condition. You have just a bunch of points with some possible limits.
Yeah, in general, I think it's going to be a little bit complicated because, well, if the space is connected, then I'm not sure how can you see you can easily describe this as some kind
I
of.
think that this condition is equivalent to being zero-dimensional, but I'm not so sure.
Yeah.
If it's generated by finite projections, yes, but if you want to try in the general setting, how can you describe this continuous function or compact outer space as being a universal system? I don't know how can you go and try to do that. Yes.
Because the only thing I can imagine is just set of points with some accumulation points, right? Tomek, what?
It's more complicated. There's a theorem of representation of Boolean algebras by Stone, and it realizes this Boolean algebra with as an algebra of clopens, or even compact open subsets of some topological space. But the topology of the space is quite complicated.
Yeah.
It is called Stone theorem, yes? Stone duality.
Yes.
Stone representation, yes.
Yeah.
But it is about Hopf algebras, so Boolean algebras, which are bounded distributive lattices with the negation. Yes. But if your algebras are not unital, I'm not so sure about the relation between this Stone representation and these algebras.
Yeah.
So the spectrum of this algebra could be more complicated even than the Stone space.
Yes.
Because it could be not compact.
Yes, sure.
Even if it's not compact, at least in the zero-dimensional case, we can still do that because you can consider just relative complements instead of looking at complements. And I think the theory works out fine. The problem is that if it's not zero-dimensional, what can we do? And that's something that I try to think about, because the Stone duality generalizes for duality between the sober space and the spatial frames. And then I was trying to think if you can define a universal system algebra of a frame in general, instead of looking just at Boolean algebra. But then you have these infinite joins. I'm not sure how can we interpret infinite joins as a relation in the system algebra setting. It's something that I've tried to think about it. I didn't go any place.
So you are talking about the property of frame, because in the definition there is a completeness condition.
Yes.
Yeah, which needs this infinite combination.
Yes. So how can you talk about these infinite joins in the system algebra setting? I'm not really sure. And also, if you look at the if you look at the duality in the sense, then the elements of the frames are actually the open sets of the topology, and then really we don't have elements on the system algebra to have ideals. So that's something that I also try to think, is there some kind of universal system algebra where instead of looking at the relations on the elements of the algebra, some kind of relations on the ideals of the algebra. I'm not really sure. So that makes much sense, but it's something that I've been trying to do, but so far I haven't done anything possible. I don't know how exactly we can go from there.
But it's a nice idea.
Yeah.
And why is this relation, this R0 relation so complicated? So somehow naively thinking, I say, okay, I have some constants, I have finite set of projections, and that's it. But you have this double sum, you have this double indexing, IMN. Why does it have to be in this form?
It's just because when you take the algebra generated by projections, what we do is you take all the products of the projections and all linear combination of products, and then you take the closure of the set. So that's one way of looking at this subalgebra generated by these projections. And here what we're looking at, just this linear combination being equal to 0. So it's the elements in the, let's say, when you take the span, if you can think and the free, let's say if you take the pre-algebra generated by this KYs, it's just the elements that when you represent the free algebra inside A is going to be 0. So this is what we want as being the relations. It's kind of all relation that's already satisfying this system algebra.
So sorry, in other words, for a general elements, you would have something like a polynomial in 3 variables, but here these QIs are projections, so you don't need to use any power of this. You also don't need to use any star of this. So
yes.
you are only left with a linear combination of finite products, yes?
Yes.
Mm-hmm.
So yes, of course. Yes. Okay.
So this
Thank
is
you.
the most general polynomial relation.
Yeah.
Yes, which simplifies to this. Mm-hmm.
Yeah, I'm sorry. Well, my mistake was I forgot that these projections are not necessarily mutually orthogonal. Sorry.
No, yeah. In this case,
that's my mistake. This is sort of my confusion. Thanks.
Okay, so every commutative algebra for projections is universal respect of these relations. And now we want this algebra generated not only by the projections, but also using some partial isometries, which is, for instance, the case of graph system algebras. And usually when we have this in the setting, if you want to prove the gauge invariance, gauge uniqueness invariance theorem, we also have an action of the circle on the algebra, which leaves the projections invariant, and we multiply the partial isometries by the element of the circle. So we can have this kind of gauge action on the algebra. And then we kind of want to find out the relations that we need to define the system algebra. So that's what we do here, is that we take this set N, which is going to be all this should be interpreted be the semi-group generated by this element here. So all finite words on this set, and we want all the invariant words with respect to this gauge action. So for instance, if you look at the graph system algebra again, let's say you have SE star, for instance, this is a projection which is not necessarily in the original projections, in the set of the original projection, but against a projection which is invariant with respect to this gauge action. So we take all finite words which is invariant, and we suppose that for every finite subset of this set of words, and the subalgebra generated by this Y is finite dimension. Again, this is really motivated by the gauge invariance uniqueness theorem. If you go to the proof there, this is something that we use this there for the proof. And then that's the relation that we're going to try to find here. So suppose you have this algebra generated by this setting, which is the case for graph system algebras. And then, okay, we want to define the relations in order for the system algebra to be universal. So we take, let's say we take, again, projections with respect to the same projections that we have already generated in the algebra. And we're going to have some partial isometries, again, for each of the partial isometry already indexed by the same indexes of the original system algebra. And we went, well, we have this map of the pre-star algebra. Just take projection, partial isometry. And we want to describe what relations that we need. And basically, the idea is that we want, we want to look at the linear combination of elements of the set N to be equal to 0. So that's the relation that we need to find to describe the system algebras. That's going to be enough for relations to describe the original system algebra. So again, we have the same type here. So this map that we build there going to be factored through an isomorphism between this universal system algebra and the original system algebra. So our idea was that. So let's
wait. So I understand here again. You have through an isomorphism.
Yeah, true.
Right?
Yes.
And can you remind me phi again? How phi is obtained? Phi is what? This map phi. I missed somehow.
Yeah. So phi is the map that comes from
I got it. Given by. Okay. Yeah. Thank you.
So that's the idea. So you have a system algebra which is generated by projection of partial system relations. Let's say you have these infinite sum relations, and you want to describe using finite sums. And then the idea is that we have to find this gauge action, and you have this condition that this subalgebra generated by finite families of words, which is invariant by the gauge action, is finite dimension. And then if that holds, then the original sister algebra is a universal sister algebra if generated in just using normal relations. And that's one of the examples that we can give is, let's say we are back in the 90s and we want to define the graph sister algebra, but we want to allow for infinite sums. So the idea is you take I'm going to use this infinity just to differentiate for the sister algebra. It's already described. But let's say we want to define the graph sister algebra as usual. So we have the universal sister algebra with partial geometries and multi-partial orthogonal projections. But we want to allow this sum whenever the vertex, as long as it's not a sinc, and we allow this sum to hold. And if this set is infinite, then this is to be interpreted as being the strong operator topology. Then what the theorem above says that, okay, you can define using infinite sum, but you can also describe, if you want it, using only finite sums. Of course, this is kind of redundant nowadays because there's already a definition of the graph sister algebra using finite sums. And as we prove for the XLAC algebras, we can prove that these two things are actually the same. So this is for this example is kind of redundant, but the idea is that let's say for the case of integral domains, that's something that is still a product that is in the future that we want to do. Let's say we want to define a sister algebra of an integral domain without that condition that Huxley used. Leah already has a definition there, but we want to work with a different kind of definition. So allowing some kind of infinite sum there. So the idea is that we can define using infinite sums, but if you wanted, of course, using some conditions, we can rewrite this using only finite sums.
So I have two things. One is trivial. I guess you are missing do, right? How to do this?
Yes, yes.
The reason I'm so picky is that after your talk, I want your slides with corrections. Yes. So I'm already pointing them to you. But that's of course not important. What I'm confused by is, of course, it's something you can prove under some assumptions on your graph. But since you are making absolutely no assumptions about your graph, I'm missing the relation that say S. It's hard to write with a mouse, but okay, say SE star, SF is equal to 0 if E is different from F. Because,
yes.
Because, you know, under some assumptions on the graph, it follows. I forgot which ones, row finite or something. But in general, you have to assume it. It does not follow.
Yes, because you don't have the relation for all vertex. Because if you have two edges which are living the same vertex, which is an infinite emitter, then because you don't have this relation, you don't have this orthogonality. But so because here we do.
Okay, I'm very happy. This is very interesting. Yeah. Okay, I've got you. Yeah. Yes, thanks. Yep. That's exciting.
Yeah. Yeah, so basically that's what I hope I didn't go too fast, but that's what I had to talk today. Thank you.
Thank you so much. Wait, I should say obrigado.
Yes, that's correct. Yeah,
that's my Portuguese. Okay, guys. Any further questions? Adam, Tomek, whoever from Zoom.
Yes, I have a question. So usually one encounters algebras generated by projections when one deals with von Neumann algebras, but here you are working with in the C-star context. So how the theory of von Neumann, how your theory applies to von Neumann algebras? Is it somehow compatible with it, or?
That's Because I'm not really familiar with polynomial algebra theory, but as far as I know, it's polynomial algebras are always already kind of represented, and then yeah, I'm not sure if there's
an abstract version of a von Neumann algebra. So it is called W star algebra, and the condition is that it is a dual of some Banach space. But I'm asking this question since generating something in the sense of a von Neumann algebra is much, it generates much more. So you can take a von Neumann algebra which is generated by one element, but as a von Neumann algebra, you would get something which is usually non-separable, like L infinity and something like that. So I wonder how this can be compared to your results.
Yeah, but I'm not sure exactly. I'm not really familiar with this in the von Neumann setting, this algebras in using generates and relations. And that's something interesting to look at.
Okay, anybody else? Tomek, Richard, George, whoever. No volunteers? Okay, I see no raised hands. You guys, you're happy? Okay, so let's thank Gilles again. Thank you so much.
Yeah, thank you.
So let me stop recording, but please don't go away.